as you guys move forward. Some of you will. Some of you will wait till the night before to write your draft, but that's fine. Hey, I'm realistic. But to save you headache down the road, from most of you, about half of the class has turned in ideas. There's been a larger percentage than I expected in the idea that didn't review the instructions, is my assumption. And so they didn't actually tell me everything that was required. Most common was they would leave their sources off. And that was part of it. So I wrote back, if you did that, responded. Just said, you can still send me your sources if you didn't. Another concern is it gets exciting. And you want to imply different physics principles, which you are more than welcome to employ in your paper. I asked you to discuss one main fundamental physics principle and focus on that so that you can cover it well. Because if you're a superhero or villain is going to follow the laws of physics or break them, again, I've had people ask me that. Yes, they can go against them as the instructions state. The idea is just to show me that you understand that one fundamental physics principle, what it is, what it means, and this is how he follows it, or she breaks it. And justify or not, you know. That's fine with me. If you start taking on too many fundamental principles, though, and that's part of your superhero, you're going to need to explain those, and you might find you don't do that sufficiently. So just be careful if you start employing too many things. Does that make sense? That's it. That's what I got. I'm excited. This is my favorite part, hearing all the ideas, because with the names, and ooh, I look forward to reading lots of these. That sounds interesting. So.
Finishing mine, when does it do technically? By midnight?
I just said today, so yeah, email me before the day's over.
So just the ideas?
Yeah, it's the idea. So you need to name, well, I asked for the name of the superhero, what their powers are, / fundamental principle, that idea, and sources, or at least a good chunk to show that you're not just making this up right now and have no idea whether or not it'll work for you. And if you adjust those and you end up not using one of those sources and you want to add others, by all means. I just want to see that, hey, you have it in your head, you've thought about this, you're not going to get stuck later because you can't find any information. I'll be okay with that. Just let me know. I just don't want you to get stuck. It's always better if you're thinking of these things, even if you don't write anything at all for a while. If you got it in your head, when you see things, you'll get ideas. Again, the next deadline will be for your rough draft, where you'll need your paper written and peer-reviewed by someone. And again, that's the deadline. You can do that anytime. So if it's easier for you to get that done ahead of time and have more time for revision or other homework and classes, by all means, bring it to me. But the next one will be that deadline. You can last get credit for doing that rough draft.
By sources, do you mean like scholarly articles?
Any source, any valid source. That can be a textbook, me. You got a boyfriend that's in a physics class? Okay. You got a girlfriend that's a physicist? You can even use Wikipedia. You can use websites. That's why if you're doing things like that, you want to make sure, is it reputable? And as stated in the instructions, which is another common thing people get docked points for, when you're citing your sources to justify what you say, you're not copying. Read it, assimilate it, put it in your own words, but give them credit because that's where they helped understand it. But tell me specifically where you got it. So just saying our textbook, when you turn in your final paper, it's okay now. When you turn in your final paper, tell me exactly what page number you're on. If you're on a website, tell me the exact URL. Not just, at hyperphysics.com, I learned where in there. That's a big site. So as long as I can specifically go right to where you were reading and check on it. If you're too vague, be more specific. So that is another comment about the sources. Yeah, I remember in English class how you cite in the bibliography or the works cited using the MLA style versus the blah, blah, blah. As long as there's enough information there in any format. Footnotes are fine. So, a lot of people will just put a number, like a subscript, number 3. Look at reference 3, and then in the back they'll say it. But you can do it at the bottom, I don't care. Just as long as where you've got all the information, I know exactly where you're at. I can go there and find it. Just think of it if it was your source and you wanted credit, what would you want people to write about you, right? But yeah, it's more about the physics content and learning how to reference and research a little than it is about, you need a semicolon here, and this should have been for... Yeah. Any other questions about it? Okay, another logistics. We're on chapter 16 today on heat transfer. So we've done liquids, we've done gases, we've introduced heat and temperature, and now we're going to start moving it around. And this is the last chapter on this unit. I did not make the test before the spring break, and I didn't make it right after either. We won't have it Monday, but we have one more lecture on heat transfer when you come back. Then we'll review, and then we'll have the exam. So you have a week to kind of get it back in your head, for those of you that won't think about this one iota while you're gone. But just be aware of that. It's coming up. We're nearing the end. You do have homework over chapter 15 due Sunday. But not 16 yet. That'll be after the break. But it's there for you. You can start it, obviously. Woo! Okay. I wanted to say a few more things about water and ice and review that we ended with last time, because it's just cool. Literally. Boom, boom, psh. Okay. So, again, when you're answering these questions, thinking about these concepts, some of you feel like you got it. Sometimes, though, you might get confused, or it'll be a new application to it, and you're like, oh, I don't know where to start. My suggestion is, for most of our thermodynamic discussion, this is our guide to thinking. So, some of you are more analytically minded. So consider these type of things. And I'll try to refer to this when I'm asking you questions. So heat equals how much mass you have, how much matter is involved, the type of matter, the type of material, and its resistance to wanting to change, that specific heat capacity, and the difference in temperature. So if you have a temperature difference, heat will be transferred from hot to cold naturally. If this is bigger, in chapter 16 they refer to this as Newton's law of cooling. The bigger the difference in temperature between two objects, more heat will flow. And the larger this difference, it'll happen faster. I mean, it's kind of, they make it sound like a big fancy law. I always thought it was more of a duh myself. Well, yeah, if one's hotter and one's colder, and you make this one even hotter and this one even colder and put them together, yeah, this will cool off even faster. As it cools off, the difference between the temperature gets closer together. There's less of a difference. And so the rate that it cools slows down. But you can kind of see that here. This helps us remember that. Likewise, if you input heat, if you put two different objects in the same fire, right, on the same stove, you're applying the same amount of energy to it, you can look at how the temperature will change based on how much of the substances you have and what they are. If you got the same thing, but more of one, this is bigger, right? So it won't increase its temperature as quickly. Yeah?
So would it be faster to boil multiple small pots of water and then add them together, or one big pot of water?
That's a great question. It's a great question. I've never had me ask that. So would it be faster to take all your water at once and boil it? or a bunch of individual little ones? If you could apply the same heat, yeah, at the same time, to all of them, given that they're all water, so that shouldn't matter. You're trying to make the same change, get it to 100 from room temperature, so that's going to be the same for each of them when they hit boiling. But yeah, if you have less water, it should change its temperature more quickly. So yes, you can boil a smaller amount of water. It gets to boiling quicker than a larger amount. So yeah, they would all get to 100 degrees Celsius quicker. Then you could mix them.
Does the change in surface...
I'm disregarding the container, but yeah.
Yeah, that's where I was going to go. I was going to say the additional surface area from the container transferring more heat. Doesn't it also speed up as well?
Yeah, you'd have to, in practical application of this, each of these little amounts of water would have to be in their own containers, and now you have to deal with them also, and that will affect things some, yes. And the size of your pot matters. You got a small pot versus a really big pot, there's more surface area. Let's say you had the same amount of matter of steel, but you spread it out so it was really thin, so it covered more area. That will affect the transfer. And that's part of chapter 16. It's the second half, but since you bring it up, it's conservation of energy. I told you already that everything gives off heat, right? Thermal energy. That's how infrared thermometers work. I can measure, the heat's coming in. This infrared electromagnetic radiation is coming to this. And it detects it, it's calibrated, and it tells me the temperature. Well, if you cool off, it can tell. Where am I going with this? Everything's giving off thermal energy because you have a temperature. Your molecules are moving. Even if something's really cold, it's still not at absolute zero, so some thermal energy comes off. Yes, Megan?
So if you had the same amount of steel in the pot, but one was like short and stout, and the other one was like tall and narrow, would the stout one boil faster then because it has more heat surface?
So something like this versus this?
But the small one would be wider because it would be the same surface area, but
Oh, same surface area.
different proportions.
Okay. If they have the same surface area and the same amount of mass?
So it's like the bigger one, the taller one would be skinnier.
Here, you come draw it.
Shorter one-
If you don't mind.
For example,
Well, that way I don't just draw it wrong again.
Forgive my proportions. So if you had a pot like this versus a pot that's half as tall but twice as wide,
Oh, there we go.
does that make sense?
Yeah. What do you think would happen?
Well, since this part heats more and the hot water would rise more, this one would heat faster. Yeah?
I'm not going to answer it yet.
That means it's yes.
No, it's more like because it depends.
Okay.
Thank you for doing that. So same surface area of material, same amount of material, let's say 2 for each, but this one, the flame can get to it more, right? So where this one may, whoops, that was bad. Maybe just one. So what you have is you got Qn. I'll do it. You're putting heat in. And I should have... Let's say they're the same burner, same type. So we're trying to put the same amount of thermal energy in. I'll just get to it. I'm not thinking of any eloquent way to do it right now. Q goes in. Does Q come out? Yeah. Thermal energy, heat is transferred out. This releases thermal energy also. I was going to ask you guys, if you guys are always, you have a temperature, if you're always giving off heat, why don't you just cool down and get colder and colder and colder and colder? In the whole universe, everything's giving off heat. Why don't we just go to a cold death and everything dies? Because we're absorbing heat also. If we're always giving it off, but we're not getting colder, we must be taking energy in.
I figured you were producing. I didn't just see it as taking in.
Well, you're producing, and where do you get that energy to produce the heat?
You're getting energy from something else.
You're getting energy from your food, right? And where does the energy from the food come from?
Everywhere else, it's
From the earth and the soil and the sun. And where does the sun get its energy? Total energy is always conserved. We've learned that. It's no different in thermodynamics. Thermal energy, total energy is conserved. And so if thermal energy transfers, it can come in, it can go out. And if you're staying the same temperature, then Q in equals Q out. That would be the temperature is constant. Right?
For example, in the big restaurants, she was asking about the pots. They have a reason why they have wider pots than taller pots. They have both. And also, when they serve the food, they have this big long line where they put the plates, and they are always, the plates are hot.
They keep the plates warm in the restaurant? Yeah.
In that way, when they get the food from the pots,
Yeah, because you know if you just leave your plate out here, it'll cool off. Because it's hotter than its surroundings, difference in temperature, so heat flows from the hot food and it warms up the air.
the same is with the ice cream. They have
The ice cream's more conspicuous.
they put the plates in the freezer, and when they get the ice cream is always
That's a good example. If the plate's already cold, then when they put the cold ice cream on it, there's less of a temperature difference. It takes longer for the ice cream to heat up and melt. So if you put the plate under a warming lamp, then it's trying to cool off, but you're constantly adding more thermal energy. And if you can put in as much as it's giving off, you can keep its temperature the same.
in the same the cappuccino machines. They have this top where the caps, the ceramic caps are always warm in there. That way, when they serve the cappuccino, because it's such a small amount of
Oh, that one I didn't know because I don't drink cappuccino. So they have a warming ceramic thing on the top of a cappuccino machine? Cool.
because the small amount of cappuccino when it comes out from the machine cools off as soon as you put the cappuccino or the espresso inside of a whole cup.
See? Thermodynamics at work. What happens to the temperature in this case? What happens to the temperature in this case? You're right. Energy is transferring to the environment. That's the Q out from some object. Yeah. Cools down. If it's losing thermal energy, because heat is being transferred out more than it's coming in, then it cools down. And the other way, heats up. So it's just that balance on Q in and Q out. Heat in, heat out, heat out.
So when someone has a fever, are they taking in more heat?
When someone has a fever, if their temperature is increasing, then yes, from various sources, the Q in is more than their Q out.
Do they also get chills?
Then something is switched. Of course, there's some physiology going on too, and chills have to do with, you can still have a temperature and have chills, and I won't go there with physiology, but that's if your actual temperature is gone up, then you have that case. That's the only way you can change your temperature, right? There's a change in temperature only when heat is going in or out. If that is staying the same, like the Q net is 0, then you're not changing temperature. Now there is one caveat. Can you think of an example where you're putting heat in? More heat in than's coming out, but the temperature doesn't change? Can that happen? Just see, give you a chance, see if you can think of something. Because maybe there isn't. let's see, temperature with time, 0, 100. Let's take water. All right. If you take water at 0 degrees and you, oh, go ahead.
I was going to say, does that have to do with the specific heat capacity of the material? Once it's heated to a certain point, it can't contain anymore, so it's forced to actually change what it is?
That's on the right lines. It wouldn't say it so much has to do with a specific heat capacity. That just determines its resistance to changing while it's in that form. But you're right. If it changes forms, now it's a different material and it has a different specific heat capacity. So let's look at water. It's a nice simple one. If you have water at 0 degrees and you add heat to it, more in than out, what happens to it? Before it steams. You got water here at 0 degrees. You heat it up, add Q. What's going to happen to it first? That's right. It gets warmer, so the temperature goes up. It expands. They're moving more. They get further away from each other. Their average translational kinetic energy is increased. The temperature goes up. That's all I was getting at. What happens at 100 degrees? It boils. So when water gets to 100 degrees, it turns into steam. And now it's changed. It has a different specific heat capacity. Ice has a different specific heat capacity than water also. But you've watched it. The water can start to boil, but it hasn't all turned to steam yet. Some of it has, but not all of it. But you're still putting heat in. So for a while, the water can stay at 100 degrees. I don't know if you've ever done it. When water gets to boiling, this is ideally too. The pressure can affect this. Water boils at slightly different temperatures here in Salt Lake than it does at the sea level. What's different about the pressure? Yeah, lower atmospheric pressure. Atmosphere is not pushing down on the water molecules as easily, so those that happen to be going really fast could escape easier than they could down at sea level because there's more pressure trying to keep them in. If you want to learn more about that, read up on vapor pressure. So that matters. But when water's boiling, it stays the same temperature until it turns into steam. Once it turns into steam, then its temperature can continue to increase. So right here, heat is being transferred to the water. Thermal energy is going in, but it's not raising the temperature. Where is it going? To air? Then it would be cooling off because it would be losing. If it's transferring thermal energy to the air, then it has to lose thermal energy. It's gaining. You still have your pot on the stove. The fire's on. There's the burner. It's boiling. It's at 100 degrees. It's transforming, but the temperature is not increasing. Wait, we're putting heat in, but we're not having a change in temperature. Where is that heat going? That's internal energy, which allows it to transform. So when the water molecule changes to steam, from liquid to steam, gas, that takes energy. So again, temperature is the measure of the average translational kinetic energy. So this heat that we're putting in is not going towards that. It's not making the water molecules move faster, bounce around like we're used to. The energy is going into different forms, maybe the vibration, maybe the rotation, breaking molecular bonds depending on the material. So it's still absorbing energy, but it's not causing the average kinetic energy, translational kinetic energy to increase. So its temperature stays the same. You with me? Same thing happens with ice. Water can stay at 0 degrees for a while. Yeah, I just did that. Nobody told me I drew this wrong. I guess the way I'm doing this, I put the temperature on the time scale. Sorry. Anyway, same idea. Once it becomes ice, now it can keep getting colder. But during the transition, the change in heat it transforms it. Goes into internal energy, not average translational kinetic energy. Do you have a question?
Yes. Do the internal observer energy have a limit?
Does the internal energy have a limit?
Yeah, because the internal and observed again has limited.
That depends on the material. Things with a really high specific heat capacity can withstand absorbing a lot, like water, because it has less effect on it. But if something absorbs too much energy, more than it can handle, and at some point it breaks it down and transforms it, then I would call that a limit. It could only take that much before it melted. So in that sense, you can look at water. If you have a certain amount of water, and it has that sort of specific heat capacity, yeah, when it gets to about 100 degrees, that temperature, then the energy that you put in, it can't hold that anymore. It goes into internal energy changes and it transforms into steam.
How do we keep getting new water drinkable?
New water?
You know, like, water's going everywhere, it seems like. So how do we get drinking water?
The good old water cycle. The water cycle always goes around. Oh, the water cycle always goes around. It goes up as evaporation, forms a cloud of condensation, comes down as precipitation. Yes, it does. Learned that one from my daughter's class, too.
I'm still in elementary school, guys.
No, that's how I remember it, see? But yeah, it turns into this. But if this cools off, it gives up energy. If it gives up too much energy, ooh, look at that, it condenses back into water. If the water gives up too much energy, it has to give up energy to turn into ice. You have to put energy in. It has to absorb energy to break those bonds and turn back into water. So it's energy in, energy out. And that's a good lesson to learn. So there are back to water. Lest you thought I got distracted. You're right, but I was going to discuss that stuff anyway. So this is good. Okay. So you got ice and water here. Let's look at volume of ice. Is that more or less than the volume of water at the same temperature? Is the volume of ice compared to the volume of water? Yeah, more for ice because it's it's less dense. It floats, so it takes up more space. So it's like here, let's say. The volume might be there. If you heat it up, it expands until you get to 0 degrees. Now we're going to have this phase change. It's going to take some time. Oh, I drew this. I did not draw this correctly because this is the time scale. But you get the idea, right? And what it should have been, still got it backwards. Okay, how should I draw this? Time is passing this way, right? It takes time for it to transition. So I had that, my gut was right there, but I drew this. This is, huh? Yeah, they're wrong. This occurs at 0 degrees. This occurs at 100 degrees Celsius. There we go. That'd be bugging me, so I had to fix that. So it heats up, it expands, the volume increases, we get to 0 degrees, but it stays at 0 degrees for a while now, for a certain amount of time, until it gets into water. As it's transforming into water, what happens to its volume? This is ice, and this is water. Here it's fixed in those crystalline hexagonal rings. When it melts, they separate and they can sloosh around. So does the density increase or decrease from ice to water? It's going to increase. They can be more compact. So we're staying at 0 degrees until it melts and changes form. That takes time. Heat is still being put in, but we're not changing temperature. It's not going into increasing its temperature. It's going into internal energy changes. Once we get to water, what will happen to the volume as we heat it up? It's going to expand too. So it goes up. This isn't a scale, by the way. It goes up. But what happens at 100 degrees? It starts to boil. We turn into steam. It stays at 100 for a while. Do you think the volume will increase or decrease? So we're changing from a liquid to a gas. Well, is a gas more dense or less dense? Less dense. That's right. Which means for the same amount of matter, it's going to take up more space. So the volume increases. I think I heard more decreases the first time. But you got that it was less dense. That's why gas goes away. So the volume increases there. This goes for a while. Then it turns to steam. And if you keep heating steam up, they'll expand, and it keeps going. So materials expand and contract with temperature, but funky things can happen during phase changes. Does that make sense? Yeah.
So if the volume increases because of the steam, why do you run out of water when you boil it? Because eventually
If the volume increases as it turns into steam, why do you run out of water?
well, because you're saying that the volume's increasing with the steam, which makes sense. But when you actually boil water, the longer you boil it, eventually you run out of water because it evaporates.
Okay, I should specify then. Eventually the water evaporates. Because where's the steam coming from? The liquid. And as the liquid transforms into steam, the steam escapes, and you have less liquid. So the volume of the water in the pot is decreasing, but the volume of steam is increasing. So yeah, I could have specified which volume I was talking about, but yeah. So if you just took ice, water, steam, I guess I should go the other way I drew it, right? Ice is less dense than water. But water is more dense than steam. And something cool happens right around here. Let's zoom in. So here's the 0 degrees. If you're all ice right here at 0 degrees and it's starting to melt, you're going to get some of this. So right now we have all of that. If some of that starts melting and you have some of this also, what happens to the volume of your mixture? You now have the slush, the mixed. Some of it's melted into water and can be more compact. So the volume decreases. This is why, because you still have some ice crystals, but some of it's turned into water, so it can be more compact, more dense. Volume decreases. At 4 degrees, all of it will have been melted by then, under normal conditions, and then it's all water. You're all this. If you keep heating it up, they expand, and the volume goes back up. So that's why that 4 is a magic number. That's the where water is the most dense.
At 4 degrees?
At 4 degrees. Because if it gets colder than 4 degrees, it starts turning into ice. or some of it can, and you have a mixture. And ice takes up more space. That's that expansion. Which is why, since water is most dense there, 4 degree Celsius water sinks to the bottom. The top stuff's warmer. If it's still winter out, it's going to get colder until it's 4 degrees, and it'll sink. And you'll end up with 4 degree Celsius water at the bottom that builds up until all of your water is 4 degrees Celsius. Then what has to happen? Can it still get colder than that? Well, absolutely. You can still remove heat from it because it's still winter. Okay, it gets colder. It's 3 degrees now on the top. Does it sink? 3 degrees is less dense, so it doesn't sink. It stays on the top and keeps getting colder and colder and colder. That's why the top of lakes freeze. You don't see ice on the bottom. If it's cold enough and your lake is shallow enough, the whole thing can freeze from the top down. But it was always top down. The ice doesn't sink and build up because of this bloated nature of water to ice transition. And thus your fish can still swim at the bottom and get around in 4 degrees Celsius water with the top completely frozen over.
Can density change? That, like same with evaporation, how it'll boil at different points. Will the freezing point change a little bit with outside atmospheric pressure?
Yes, these points, 0 and 100, change with pressure also. From chemistry and physics, we always say STP. At standard temperature and pressure. If you change those, it's the ideal gas law. Whoop. Pressure, volume, constant, temperature. They're related. So if you're changing one of these or both, then you get some different, it can happen at different things than we're used to. For example, pressure cookers. They allow it, it can boil at a lower temperature because you're putting more higher temperature. They boil at a higher temperature so you can cook your food faster. If your water is at a higher temperature, it'll cook faster. But how do you get your water to be at a higher temperature? Because at 100 degrees it turns into steam. Keep it from turning into steam. Put pressure on it so those water molecules can't escape. Then it can keep getting hotter and you can cook your food faster. But it is under pressure. So if your release valve's not in good working order, you just created a bomb. Okay.
And the water doesn't evaporate from. If you put 1 cup of water.
Yeah, you can use a lot less water in a pressure cooker because it's not turning into steam and escaping because you're keeping pressure on it.
And it keeps the same. 1 cup of water, if you boil in a pressure cooker for the same temperature, the same temperature, medium temperature, in your burner, it doesn't evaporate. After you open the pressure cooker, the same amount of water is there.
I like that. You can keep the same amount of water in the pressure cooker. It lasts longer. Same reasoning. Okay. For the last 9 minutes, I'll just introduce you to the 3 ways we transfer heat. I'm assuming most of you are familiar with these. And we'll discuss some more after break. But it's conduction, convection, and radiation. They're in your book. That's what most of chapter 16 is. And we'll discuss them in more detail. So here's another thing I learned from my daughter. Well, let me explain them first, then it'll make sense. Conduction. These are all ways to transfer thermal energy, to get from one object to another. We've been talking about this exchange. These are the methods. Conduction, you're in physical contact. You touch something, now thermal energy can transfer. And it'll transfer from the hot object to the cold object. If you're the same exact temperature, nothing will transfer. So try this out. There's a metal handle on your chair. Touch it and touch the wood. Tell me which one's colder, the wood or the metal? Most people think the metal's colder. It feels colder. But they're the same temperature. They've been in there a long time. They've had time to come to equilibrium in the room. They're the same temperature. But why does the metal feel colder? Well, it conducts heat better. You know, some things are insulating, like a styrofoam or a carpet when you get up in the morning, but you walk onto the tile floor and it feels cold, even though they're the same temperature. Heat's being transferred, but it can flow easier in things like metal and tile compared to carpet, liquids and gases. So, you're generally hotter than the metal and the wood. So, heat flows from you to those. It can be conducted better in this table. So, it pulls more heat out of me faster than it does in this case. So what does that leave your hand? With less energy than this hand. And so it feels colder. But that transfers conduction. It's in physical contact. The microscopic molecules here, they're hotter. They're moving faster on average. So they run into these and they bonk them and transfer their energy to them. It makes them go faster. Its temperature increases. Yours slow down, decrease. You get cooler, it gets warmer. That's conduction. Convection is you heat up a fluid, so liquid or gas. And the medium that gets heat up physically moves over to another object and transfers its heat or its energy. That's like a radiator or a space heater. You heat up the air next to it through conduction. But then the air is warm. And what does warm air do? It rises because of the density. It's less dense. Well, now there's cold air here. It warms up. It goes up. This cools off. It expands and cools up and comes down. And you get this convection of air flowing. That's convection. And if you're sitting over here, that warm air will come to you and warm you up. And then it'll get colder and come back, get re-warmed up, come over to you. That's convection. These like cells of fluid flow, whether it's air or water or blood or whatever. That's convection. You can transfer energy that way. Radiation is the last way, the less familiar. It requires no medium to transfer the heat. This one, physical contact, it has to go through something. Convection needs that fluid to heat up and it physically moves. Radiation can go through empty space. I'm going to turn this on. Not all of you can see it. This is like a space heater. It's a coil of wire. I'm sending electricity through it right now. It's like your blow dryer coils or space heater coils. They're going to heat up. Oh yeah, you guys will start to see them glow. And this dish focuses this infrared heat. It's in the form of electromagnetic radiation, which is why it can go through empty space. This dish focuses that over to this dish, which then focuses it onto the head of a match here. Now that match head is absorbing the thermal energy. It's being transferred to it through radiation. It doesn't need the air. Yes, this heats up the air next to it. That air goes up. So if we left this on long enough, we could heat up the room, but it would take forever. That's convection. It doesn't need the air. The energy from the sun gets to us on Earth through radiation. It's just because it's hot. You stand next to a fire, it feels hot. That's because it's radiating thermal energy. That energy you guys are giving up just because you have a temperature, you're giving off infrared radiation. That's how you're losing heat. So that's another energy transfer. So this takes a few... can you see it smoking? There's smoke. So it's working. And if that absorbs enough thermal energy, goes up, then it lights. And if you want to have fun, you tape it to a firecracker. Because all of you can't see it either, but that way you know when it happens. So we had transfer of energy through radiation. Let's do some more fire. All right, we heat up the air. The hot air goes up the chimney, out the top. Cold, fresh air comes in, heats up, less dense, goes up. So in theory, there's convection up through this chimney. Let's see. Take some paper bits, toss them in, and they ride on the air currents, which are going up. So there is convection going on.
Blue fire hotter than a red fire?
Blue fire is hotter than a red fire. Yeah, I want to discuss that. We are. I'm going to save that though for after break, because while my lava lamp is working, I'll end with it. It's a great thing. It's got all three. So there's a light bulb down here giving off radiation because it's hot. That radiation hits the bottom of the glass and the liquid, and they're touching, so they heat up through conduction. If the blob down here gets warm enough, it expands. If it expands enough, it becomes less dense than the surrounding fluid, and it has a buoyant force and comes up. The one up top is cooling down because it's farther from the heat source. If it cools down, it contracts, becomes more dense, and goes back down. So it's kind of like you see convection cells going around. Lava lamps are great for this. So, conduction, convection, radiation. That's what I learned from my daughter. Conduction, physical contact. Convection, those convecting cells, V for vection. Radiation, it just is emitting infrared radiation. Conduction, convection, radiation. There you go. Get that stuck in your head all break. Have fun.